Okay, so the last talk of this morning session is going to be by Cécile Repellin, who is from the University, Grenoble, Alpes, and she's going to be giving the second part of her lecture from yesterday.
Yeah, thank you very much. Okay, I need this and this. Okay, right, so hello again, everyone. So today we're gonna pick up where we left things yesterday. So yesterday we were talking about moire materials from a single particle perspectives, and we talked about how flat bands could emerge in these materials. And the main reason I think we're all very excited about these materials is this possibility of flat bands, because when bands are flat, this gives the possibility of having strong correlations. So now we're going to add strong interactions and see what kind of physics we obtain. So as you've understood, we're focusing mostly on quantum Hall-like type of physics. There are many other strongly correlated phenomena that are arising in moire materials, and they will be beyond the scope of this lecture. So here, yeah, we will be focusing on quantum Hall physics without a magnetic field in moire materials, namely quantized anomalous Hall effect, integer and fractional. Right. Yeah. So this is the outline of the talk essentially. So yeah. So we'll start with some things. We'll start with some introduction first, and then talk about something that's often called quantum Hall ferromagnetism. It's a type of flat band ferromagnetism, and then and it occurs typically at integer filling of Landau levels or flat bands. And then we'll move on to fractional channel insulators, which occur at fractional filling of Landau levels or flat bands. And yeah, so a good place to start is Landau levels. So we've just had a lecture about anyons that had a focus on the fractional quantum Hall effect. And so this is going to sound familiar again, but there's going to be a strong analogy between these Landau levels and the flat bands of moire materials. So let me review just a few things about them, about the quantum Hall effect. So the quantum Hall effect, typically, in principle, you expect it in a two-dimensional electron gas, so which you can obtain either in a 2D material like graphene or in semiconductor quantum wells, where electrons are effectively confined to 2 dimensions, when you have a strong magnetic field. So let's say there's a current going in this direction, and because of the magnetic field, there's also going to be a Hall, like a transverse voltage, so a voltage in this direction, not just the direction of the current. And if you're in the classical regime, if the temperature is somewhat large, then the Hall resistance is going to be proportional to the magnetic field. But here we will be even more interested in the case where it's actually quantized and doesn't behave classically. So this is the quantum Hall effect, where the Hall conductance, which is just the inverse of the Hall resistance, takes quantized values, so integer for the integer quantum Hall effect, or fractional for the fractional quantum Hall effect, values of the quantum of conductance E square over H. And this occurs when you reach the quantum regime of the Hall effect, meaning that your temperature is low enough, your magnetic field is large enough, and you are in 2 dimensions. And as we've just heard from Fiona in the last lecture, one of the main reasons we are very excited about this question of the fractional quantum Hall effect is that it's a strong correlation problem, and it leads to very exotic physics that we wouldn't get otherwise, namely the possibility of having anionic excitations. So excitations that don't behave as bosons or fermions, but have a fractional statistics. Associated with this question of the quantum Hall effect is the Landau levels. So Landau levels are the spectrum that you obtain when you have a charged particle in a magnetic field and that this particle is confined to 2 dimensions. So just the single particle quantum Hall problem for electrons, let's say. So these Landau levels are energy levels. They are perfectly flat, as has been emphasized before, and they're separated by one another by a relatively large gap. And if you're in a, let's say, gallium arsenide or something with where the electrons have a mass, then the gap is going to be the same every time, and it's equal to the cyclotron frequency. Right, so each Landau level has a degeneracy, and this degeneracy is going to help us fix the filling fraction. So the degeneracy was also worked out in the previous lecture. That's nice. And it is equal to the number of flux quanta that pierce the sample. And because of that, it's proportional to the area. So it's an extensive quantity. So it's really macroscopic. And what we call the filling fraction is how many Landau levels am I filling up? So nu equals 1 would mean that I'm filling for spinless particles, just for simplicity. Nu equals 1 would mean that I'm completely filling the lowest Landau level, or nu equals to the second one. Right, so this situation is what gives rise to the integer quantum Hall effect when you have an integer filling fraction. But you can also have a fractional filling fraction, so a partially filled Landau level. And this is going to give rise, for some very specific fractions, to the fractional quantum Hall effect. And you see that if I'm partially filling a flat band, if I don't have any interactions, I have many, many ways to do this. So interactions now are going to become really crucial to understand this phenomenon. So now the question is going to be, there's all these very interesting phenomena occurring in quantum Hall physics. And we know that we have Chern bands that are flat in moire materials. So in a sense, they really are analogous to Landau levels with some modifications that we'll talk about. But they're really analogous to them. So could we have a fractional quantum Hall effect, and could we have all of the phenomena that we have in quantum Hall physics? So let me maybe just summarize a bit the type of flat bands that we have in moire materials, or more specifically the ones that I've introduced in the first lecture, because of course there are many more. So in what we saw yesterday is that in magic angle twisted barrier graphene, you essentially have 8 degenerate flat bands. And if you have a substrate that's well aligned with one of the layers, that will generate a gap that decouples those 8 bands into 2 sets of 4 bands. And importantly, among all of those, okay, more battery maybe. Among all of those, the 2 bands have a Chern 1, 2 bands have a Chern -1, and same thing for the valence bands. Now in twisted TMD, the situation is, well, I guess the degrees, the overall space is much reduced because spin and valley are locked, and you're starting from a single band to begin with. So you often have, you can often consider a band that's twice degenerate with Chern 1 for one valley and Chern -1 for the other valley. And in analogy, you have the lowest Landau level, where again you have a twofold degeneracy, but this time the Chern numbers are 1 for both of the Landau levels, because both spins have the same Chern number. And so very often it's convenient to do a projection into the lowest Landau level. And this is this is what we're going to do. Essentially, you're going to say that interactions are strong, and they are, but they are not as strong as the gap between two Landau levels, so that you can project out all of the other bands. And that simplifies the problem somewhat, but now you only have one scale of energy, which is the interaction. So it makes it really obvious that it is a strongly correlated problem. So the approach for marine materials is going to be very similar. You're going to try and reduce your problem to a single band and project interaction onto that flat band. So this would be justified, strictly speaking, if the bandwidth is much smaller than the interaction strength, which is itself much smaller than the band gap. Which may not always be really true in materials, but you have to have a starting point. And you can also reintroduce the bandwidth if you like. This is not really a problem, but having more bands is, of course, more degrees of freedom, so it's more heavy from the point of view of calculations, for example. Right, so if I can write down more explicitly the Hamiltonian, the projected Hamiltonian, the single band Hamiltonian, like so, in blue, where this is the sum. I can write it in momentum space now that I've done the projection. So this is a sum over momenta of V of q, rho q more minus q, where V of q is simply the Fourier transform of the interaction. So if you just have Coulomb, this would go like 1 over q, or this could be a bit more complex if you take screening into account or other things. And then rho q is the projected density operator. And it is the sum of projected operators for different internal degrees of freedom. So the sum for all the values and all of the spin. And if I'm considering just one flavor, so one value, one spin, then this is how it writes. So you recognize so it's a sum over k of a form factor times c dagger k c plus q ck. So you recognize that it's a density, but you have this form factor which consists of overlaps between the single particle wave functions in the flat bands. So, and that's what's going to give the particular physics of the flat bands, right? Otherwise, all flat bands could be the same, but that's what makes one flat band different from the other, this form factor. So let's pause a little bit and describe the difference between the Landau level and the flat band, because we've talked about the analogy. Let's say how they're different. So as we've heard from the previous lectures, and specifically some of Joel's lecture, we can define some geometric quantities in a band, and namely here the quantum geometric tensor, where the d here is the covariant derivative. So U is again my single particle eigenstates in the flat band, and I can decompose this tensor here into a real part and an imaginary part, and the real part is the quantum metric, and the imaginary part is the Berry curvature. Right? So to describe a geometry, you always need a metric, meaning you need a way to measure distances, and you need to know what is the curvature as well. Right. So quantum metric, G is the quantum metric, omega is the Berry curvature. And the Berry curvature is related to a topological quantity, the Chern numbers, through an integration of the whole Brillouin zone. So one key aspect of Landau level, one key specificity is that both quantum metric and Berry curvature are independent of K. They are completely homogeneous in the Brillouin zone, if you want to define a magnetic Brillouin zone. So, what about the projected density operator? What happens to it? So in the Chern band, you can relate the form factor that defines your projected density operator in terms of these geometric quantities if you do a small q expansion of your form factor. So namely, A here is the Berry connection. So if you take the curl of A, you will get back the Berry curvature, and G here, over there is, again, the quantum metric. So I could put that back into an exponential if I recognize the beginning of the expansion of at small q of an exponential, and see that essentially what's going on is that the quantum metric is describing how fast the interaction is decaying in k-space. And the Berry connection or Berry curvature is describing how it's winding, like how its phase is behaving. Right, so this is especially this quantum metric thing is described, it comes in addition to V of Q to say how interactions are decaying with Q. So what this means now is that through this form factor, because Berry curvature and quantum metric are not homogeneous in K in a generic Chern band, the interaction strength is not necessarily homogeneous in K. And this is very different from what happens in a Landau level, where you have this, it's like no use. You have a decay as well as a phase, again, so in strong analogy with the Chern band, but this time the decay is the same everywhere in the lowest Landau level. So your interaction is homogeneous in the lowest Landau level. And if you think about it, if interactions are not homogeneous, in the regions where the electrons feel like they're further apart from each other because of the metric, they're going to experience a smaller interaction, whereas if they feel like they're closer together because of the metric, then they're going to experience a stronger interaction. And because of this homogeneity, possibly you could create some symmetry broken phases by exploring some parts of the Brownian zone rather than another. Right. So let's go to some more concrete things and see how that will influence the many-body physics. And let's talk about quantum Hall ferromagnetism. So earlier, I gave you a simplified version of Landau levels where I didn't have spin, but now I'm going to have to include spin. And in a naive picture of the quantum Hall problem, you could say, oh, but I have a strong magnetic field, so my electrons are all going to be spin polarized anyway. Spin is not a relevant degree of freedom. But this is not true because of these energy scales, essentially. So the Zeeman energy, which splits the Landau level into two, is actually quite small at typical magnetic fields used in the experiment compared to the interaction strength, E square over epsilon LB, which is itself quite small compared to the cyclotron gap. So this last thing, so the interaction being very small compared to the cyclotron gap, we've already said, and this is what justified the projection to the lowest Landau level. But the second one, or the first one, Zeeman energy being very small compared to interactions, means that you cannot start from a spin polarized Landau level. You're going to have to consider both spins. And sometimes you could even make the approximation that Zeeman is zero, and that this is you get interaction effects. So in practice, it means that when you're looking at the quantum Hall effect at μ=1, even though the ground state is a product state, so it's really a Slater determinant, so it's a very mean field problem in a sense, but it's really coming from strong interactions. And so this is a state that is spin polarized. So the initial intuition, the naive intuition, if you want, was right, but from the wrong reason. It's spin polarized, but because of interactions, not because of Zeeman. And maybe one way to understand this, where it comes from, is so we can say that Coulomb interactions actually result in an effective ferromagnetic spin exchange. And one way to understand this is as an analogy to Hund's rule in atomic physics, which tells you that if you have degenerate orbitals and you have a way of completely filling a shell with spin polarized electrons, then this will be more energetically favorable than doing up, down, up, like the other configuration in the bottom. So if you generalize that to a flat band, which is just the same thing but with more orbitals, then you would obtain a spin polarized state. Another way to think about it is to say, well, if my wave function so my overall wave function has to be antisymmetric, but the spin can be fully symmetric, and then the spatial part will have to be antisymmetric, which will create nodes which will screen better the Coulomb interaction. So I will gain in terms of Coulomb interaction by having spin polarized electrons. So this is a generic argument. I didn't use the fact that I had Landau levels to say that I should have some exchange. So it should occur in flat bands. And indeed it does and has been observed experimentally. And I think the first time it was observed was in magic angle twisted bilayer graphene aligned with hexagonal boron nitride. So the case where we do have a substrate-induced gap between the two sets of band in TBG. And the way this is seen was first through a hysteresis of hole conductivity, which indicates a Valley polarization, right? So you see that even at zero field, there's a non-zero hole resistance. In the first experiment, it wasn't quantized, but yet it was there. And as you reverse the sign of the magnetic field, you go through a whole hysteresis loop. And this is occurring because here you have it's not because of the polarization of the spin, which is SU2, but because of the polarization of the Valley, which has to, reverse which can make domains because it's like an easing degree of freedom. Right, so this was occurring at nu=3 in TBG, and not very much later, the group of Andrea Young observed a quantized anomalous Hall effect in the same type of material. So TBG at magic angle aligned with hexagonal boron nitride, and now there is quantization of Rxy to h/e square. Right, so this quantized anomalous Hall effect comes from the fact that, first of all, we have Chern bands, but as we've seen previously in the single particle models, there's no breaking of time reversal symmetry. So time reversal symmetry breaking here is a spontaneous phenomenon that's coming from interactions. And yeah, I just wanted to point out that previously Coulomb anomalous Hall effect had been observed, but only in systems where time reversal symmetry was broken explicitly through a doping with magnetic atoms. Right, and now we have several more examples of quantized anomalous Hall effect in moire materials. One of them is twisted bilayer TMDs, so twisted MOT2 in particular. And so here are some of the experimental data, maybe some of the easiest to understand because it's, again, a hysteresis of the Hall resistance accompanied with a zero, a vanishing of the transverse resistance. And again, this is occurring because you're fully polarizing your electrons into one valley, and as you reverse the sign of the magnetic field, you will polarize into the other valley and get the opposite Hall resistance. It's also observed in other moire materials, such as heterobilayer TMDs and rhomboidal graphene, for example. Right, so now I've given you some intuitive arguments about quantum Hall ferromagnetism, and now I would like to give you some maybe more concrete analytical arguments. So we're going to consider a flat band, and with a projected interaction Hamiltonian, such as the one written above. So it's still the same Hamiltonian, generic Hamiltonian that I wrote in introduction. It's just an interaction projected onto a flat band, where V of Q is the Fourier transform of the interaction, And rho Q is the projected density operator and which has terms for the different flavors of spin valley or whatever it is. And it consists of these form factors times C dagger K plus Q C K. And of course, the single particle wave functions of the flat band UK can be analytically known if you are in the Landau level, but if you are in a moire material, typically you'll have to do numerics and to find them either from a continuum model or from something maybe more realistic that you obtained with DFT, let's say. Right, so here is my argument now for quantum Hall ferromagnetism. So first of all, we are going to notice that this particular Hamiltonian is positive semi-definite, meaning its spectrum consists only of positive energies. And this comes from the fact that V of Q is positive. So it's definitely positive for Coulomb interaction. And then the other thing is that rho Q, rho minus Q can be rewritten as rho Q dagger. And this is a generic properties that of adjunct operators that if you have A times A dagger, this is positive semi-definite. So your Hamiltonian is now just a sum of terms that are all positive semi-definite. So it is positive semi-definite. If you're worrying about normal orderings of field like this, normal ordering is going to add an extra dispersion term. And I can always, my assumption is to have a flat band. So I can say that I'm including the normal ordering into that assumption of a flat band. Right. So, and the next argument I need is that the ferromagnetic state at integer filling. So let's say nu equals 1, for example. The flavor polarized state is a zero energy state of this Hamiltonian. So why is that? So you can easily notice that if you apply the projected density operator onto that state, this spin polarized state, you will get 0 unless Q is 0 or a reciprocal lattice vector. And that's just because of the Pauli principle. Because, okay, let's imagine you have your band that's fully filled with only one flavor. And now through these C dagger K plus Q C K operators, you're taking out one electron at K, putting it back at K plus Q, but K plus Q is already occupied unless Q is 0. So it has to be 0. So because rho Q psi is 0, then H psi is also 0. So psi is a zero energy ground state. Is a zero energy state. And because the Hamiltonian is positive semi-definite, it has to be a ground state. Of course, I didn't prove that it has to be the only ground state. I'm just saying it is a ground state. Right, so let's note that we have, in doing this argument, we've neglected some terms, which are because the sum above in the blue Hamiltonians it's not limited to the first Boolean zone. It goes over all possible values of Q. So possibly you could have terms at K equals to a moire reciprocal lattice vector, and that would spoil my argument. But typically we know that the form factor here decays really fast. So those terms should be really small in principle. Right, so yeah, just maybe one more comment about this whole argument, which what's nice also about this argument is that I'm not assuming any topology here. So I didn't say I had a particular geometry or particular churn band. So it could happen in a trivial band in principle. But there's a caveat, which is that if you take a trivial band, that trivial band could be an atomic limit, for example. So if now I'm starting to take all of my atoms apart, I will have just no coupling at all. And then all states at different spins will be at the same energy. And So that means I don't really have a ferromagnetic state. So it would still be true, like the ferromagnet would still be a ground state. It's just there would be a lot of other ground states. There wouldn't be any spin stiffness. So, but on the other hand, if I take a trivial band from the point of view that it has strength 0, but it's not an atomic limit, it's coming from the interference of various bands, then I might get this effect still. All right. So if you want to go beyond flat bands, then you need to do some numerics. And what a lot of people have done is to treat this problem at the mean field level and do some Hartree-Fock calculation. And this actually works quite well because at integer filling, the integer spin polarized state is a mean field state. It's a product state, so you can capture the physics there quite well. There is a tendency of this method to sometimes overestimate the stability of ferromagnets, but still it gives you some pretty accurate estimates. And otherwise, if you don't trust Hartree-Fock, you can do exact normalization as well, which I did. And so this is an example at nu equals 1 of various moire models, either TBG aligned with HBN or twisted double bilayer graphene, twisted trilayer graphene. And some of those, depending on which parameters you're using, have different churn numbers. So this is the C that you're seeing on the left-hand side. And so what I'm showing here is how much bandwidth does it take compared to the strength of interaction to kill the ferromagnetism. And okay, so you see that roughly it takes between 5 and 10% of interactions for the bandwidth, for the ferromagnetism to be killed. The x-axis corresponds to 1 over the number of moire unit cells. So it's a thermodynamic limit extrapolation, right? It's exact normalization while you're considering all possible spin polarization, so you cannot really go to really high system sizes. Yeah. Okay, so the question was about Landau level mixing, if there is any qualitative difference from, in exact normalization. So I think, okay, how do we put this? I think you want to include Landau level mixing at the, maybe at the mean field level first to see how it normalizes your bandwidths and your single particle wave functions so that you can end up with a single band, because doing ED with several bands is just too prohibitive. So I don't know of any works that actually did it with multiple bands, because also I think people think of this as a pretty well understood phenomenon. So doing something as strenuous as including more bands to know if there's a quantum Hall ferromagnet I don't think is in a lot of people's minds. But in moire materials, though, it would be very important, and some of people have done it, and especially when you do Hartree-Fock, it means you're taking into account the contributions from other bands, and those definitely will normalize the single band, the single particle band property. So energy, bandwidth, etc. In graphene. Sorry, you said the SU4 what? You mean in single layer quantum Hall graphene? Sure. Okay, yeah, that's an extremely subtle question. Okay, so the problem you're thinking of, single layer graphene so the zeroth Landau level in graphene has this SU4 symmetry. So from the generic arguments of quantum Hall ferromagnetism, you know that you will obtain something that is an SU4 ferromagnet, but that doesn't fix the problem because there are like 4 phases of this SU4 ferromagnet. And then you need the extra term in perturbation theory to actually pick out which of those it is. And indeed, there are, it's thinking of this Kharitonov approach, and when you have the phonons and different couplings, and what's seen in some experiments is you have extra terms that are not present in the zeroth Landau level of graphene, but do include Landau level mixing, and are explained in that way. Yes, yeah, but that's like orders of magnitudes more complex than what I'm. Yeah, it's definitely in the same sort of same framework, but much higher order effect than what I'm talking about. Sure.
So the difference. So the y-axis is the ferromagnetic limit.
No, sorry, this is the critical bandwidth at which you lose ferromagnetism. So maximum bandwidth for which you have ferromagnetism. Yeah. So the higher up, the more robust your quantum hole ferromagnet is to bandwidths. Okay. Right. Yeah. So something that characterizes how robust a quantum Hall ferromagnet is, or any ferromagnet is the spin stiffness. So how hard is it to create like a spin flip excitation? Specifically, if we're thinking, if we have an SU2 degree of freedom, like we do here with spin, then you will have, like, the spin flip excitations are going to be gapless Goldstone modes. And as long as we are preserving the total spin, then we can actually calculate the dispersion of these Goldstone modes. And because it's essentially a single particle problem within this sub-Hilbert space of one single spin flip. Right, so if you do that, you will see, and so the different points in different colors are for different system sizes, different numbers of moire unit cells, because this was done in I think TBG aligned with HBN for some set of parameters. So this is the dispersion of the magnon, if you want, so the spin flip Goldstone mode associated with the quantum Hall ferromagnet. And you see that, so at small k, this dispersion is linear in k squared, and with a proportionality factor that is connected to rho s, the spin stiffness. And so rho s can actually be calculated exactly in Landau levels because we have already analytical wave functions. But once you do it in a moire material, you need to rely on numerics, but still some authors have figured out that you can still connect the spin stiffness to Berry curvature and quantum metrics. So it's like the spin stiffness is going to be another of these examples of these quantities that is connected to some geometrical properties. So that's just okay, on the right is just a reminder of the form factor for the projected density and how it relates to Berry connection and quantum metric at small q. So if you do this expansion, and if you work at small q, and essentially you need to assume that the fluctuations of these geometric quantities are not too large over the Brillouin zone, you'll find that rho s is typically proportional to the average of the Berry curvature squared times some other terms that depends on the quantum metric and of the interaction. So it's what's interesting here is that so it's not a topological quantity, because when you integrate over when you integrate Berry curvature, it's the Chern number, but when you integrate the Berry curvature squared, it's not quantized. But still, this is going to be like this sum of the omega k squared is bounded, is always above the Chern number squared. So if you have a topological band, then it's going to make the spin stiffness larger. And you may be familiar with this argument from superconductivity, because essentially the superfluid stiffness behaves in a similar way where the topology helps to have some superfluid stiffness. And maybe this is when we need to remember what I said about trivial bands in the previous slide, that if you had an atomic limit, then you wouldn't get any, your ferromagnet might still be a zero energy ground state, but it would be generate with the rest. And this is because the rho s would be zero, which we'd see more explicitly here. Okay, keeping in mind that this is an approximation with slowly varying Berry curvature and quantum metric. Therefore, this was an interesting connection to make. All right, so this is pretty much all I wanted to say about quantum Hall ferromagnetism. So now until now I was working always at integer filling. I'm moving on to fractional fillings. And something that has been figured out is that although fractional Chern insulators, which are the equivalent of the fractional quantum Hall effect, but in a Chern band, although they are strongly correlated phases, there are some single particle quantities that we can look at that tell us whether there's a good chance that the ground state with interactions is a fractional Chern insulator or not. And so these are indicators, single particle indicators. And many of those, at least originally, were connected to Landau level mimicry. So you're trying to, so you have a Chern band. So we're considering a Chern 1 band here. You have a Chern band and you're trying to make it as similar as possible as a Landau level, because you know that in a Landau level, once you turn on interaction, you'll get the fractional quantum Hall effect. So what does it mean? It means a small bandwidth, obviously. Obviously, if the bandwidth is too large, you will not populate equally all the states. And also small k variation of Berry curvature, because omega k is the same everywhere. It doesn't depend in k in a Landau level. Same thing for the quantum metric. And also near saturation of the trace inequality. So this inequality, trace G larger than omega, is true all the time, but it's almost, so trace G is almost equal to omega. Trace G is equal to omega in a Landau level. In the lowest Landau level, sorry. And all of these indicators have been tested numerically in many, many models. So typically, this works quite well to indicate you when you will get the fractional Chern insulator or not. So much later on, so much more recently, there was another idea that was pushed forth to understand when fractional Chern insulators are stable in a Chern band. It's the idea of ideal bands, or sometimes called vortexability. And an ideal band is defined by having a saturation of the trace inequality, meaning that trace D is equal to omega. But unlike what was written above, gk and omega k are allowed to fluctuate as much as they want in momentum space. And it was shown that if trace G is equal to omega, this is strictly correct, then the single particle wave function have such a structure that you will be able to write down explicit wave functions that, maybe not explicit, but you will be able to write down wave functions that will be exact ground states of short range interaction, much like what you can do in fractional quantum Hall physics in Landau levels. So there, essentially, it's a limiting case where you have exact properties where you know that you'll have an FCI ground state. And somehow, this realization came around the same time or slightly later that than the chiral limits of twisted bilayer graphene was introduced. So if you take twisted bilayer graphene and set the tunneling from A to A to 0, then this is an ideal band. Okay, let me just set a few exceptions, not exceptions to this ideal band that I was talking about, but general exceptions to the general recipe to get a fractional Chern insulator, right? Like, so very often I would say, most of the time, if you want to find an FCI, I would say look for a flat Chern band with Chern 1 with near homogeneous Berry curvature and quantum metric, and and near saturation of the trace inequality. Still, it doesn't mean that it's a necessary condition. And you can cook up a model where you have a trivial band, and still, once you add interaction as fractional filling, the resulting many-body ground state is an FCI. Yeah. The band is fine-tuned, not necessarily the band itself, and the geometry is fine-tuned, but not the interaction. Right. So when it comes to FCI stability, single particle indicators are really convenient because then you can do high throughput calculations, but then you still need to check whether you have an FCI or not, unless you have an ideal band, which most models are not. And for that, you need some many-body calculations like exact diagonalization. And exact diagonalization is typically, well, it's limited to relatively small systems, but in the fractional quantum Hall setting, it's kind of okay because it's a gapped system, and correlation lengths are relatively small. So even in finite size, you see the features of the fractional quantum Hall state. So what is done typically is to work within one band with this Hamiltonian here, maybe introducing some dispersion or maybe not. And then you obtain the low energy spectrum in each momentum sector. And I like to use this linearized momentum index to separate all the states, because the 2D momentum is not really easy to deal with when you're doing plots. And otherwise, this is the energy relative to the energy of the ground state. And you see that you have 3 almost degenerate ground state. This is in a continuum model of TBG at magic angle aligned with HBN at filling fraction 2/3. So why this filling fraction? So 2/3, so it's the whole picture. So in the electron picture corresponding to that, this would be nu equals 10/3. And the observation of quantized anomalous Hall effects included this fraction, or not quantized, but of anomalous Hall effects included this fraction. And this is why we chose it at the time. Yeah, so you have these 3 near degenerate states that are separated by a gap from low energy excitations. And this degeneracy, this is exactly the topological degeneracy that Fiona was talking about in the previous lecture. So this is associated with this fractional quantum Hall ground state. So one more thing you need to do is to do some gap extrapolation. So you need to do several system sizes and see that what you're seeing is quite consistent. You're seeing the same patterns, specifically that the gap is remaining in black. The gap is remaining at a reasonable value that's not dropping to 0, whereas the degeneracy lifting, which is due to finite size effects, should go exponentially to 0 in the thermodynamic limit, is stay small. Like with the sizes we have, we cannot say much more than saying it's staying small. And one more thing you can do is this flux insertion that checks how the 3 almost degenerate ground state flow into each other once you insert a flux through the cycles of the torus. And it's essentially a way of finding out what is the whole conductivity of the system. And that is indeed consistent with the 2/3 E square over H. Right, so these are some of the numerical signatures are gap, ground state degeneracy, fractional Hall conductivity. And if we had more time, I would maybe tell you about entanglement spectrum, which would be an even stronger marker of topological order from the numerical perspective. Right, so what about spin polarization? So it's not necessarily something that's thought about a lot in this field, but since I spent a long time telling you about quantum Hall ferromagnetism, I shouldn't just assume that things are going to be spin polarized in the fractional case, especially because the arguments I gave you for quantum Hall ferromagnetism included that you have an integer filling. So fractional quantum Hall states are not necessarily spin polarized, and actually neither are fractional channel insulators. And one key example, which happens to relate to what I just showed you, is the fraction 2/3 in a Landau level with spin, because there are two main competing states at 2/3, both with a hole conductivity of 2/3. One is spin polarized, and this is the particle hole conjugates of the Laughlin 1/3 state, right? So this Zi minus dj to the cube, and you do a particle hole. So this is spin polarized. I didn't write it explicitly in the wave function, but this is spin polarized. So you just do a particle hole conjugation of this, and which remains spin polarized. Another option, and so Bert Halprin introduced this spinful fractional quantum hole wave function. It's a whole series of them and generalizes the Laughlin wave functions to the spinful case. And so the other option, so for 2/3, there happens to be a spin singlet with another Halprin wave function. So you have like some interspin parts and some intraspin correlations as well. It's not exactly this wave function, but it's in this universality class. And so what about fractional Chan insulators? So yeah, before going to that, I should say that those two states are actually observed experimentally in a Landau level, right? At 2/3. If you have low Zeeman, you'll get a spin singlet, but as you increase the magnetic field, you spin polarize things and you get the first wave function I wrote above. So in a Chern band without a magnetic field, I don't expect any Zeeman energy. So does that mean I should automatically get a spin singlet? Well, actually, no. And this is what we found out by doing exact vernization also. And we found that by tweaking the parameters of the model, we found that larger fluctuations of Berry curvature, or generally speaking, larger fluctuations in K of the geometric quantities of the single particle wave functions led to a phase transition between the spin singlets for the regime that's closest to the lowest Landau level. Okay, so that makes sense. So this limit here where everything is homogeneous is like a Landau level, so we should get a spin singlet there. But as you increase, let's say, fluctuations of Berry curvature, you go through a phase transition where you still have an FCI, but now this is a spin polarized FCI. And if you increase them too much, you have what I was saying earlier, which is that if this is too much, then you cannot accommodate an FCI anymore, and you just get something else. And the something else really depends on the band. Right. Okay. Okay. So that's just a kind of a comment about spin polarization in FCIs, that they also depend on the quantum geometry of the band. Not only does the stability of FCI depend on that, but also the spin polarization does. So now what about experimental observation? So I think the first hints that we could have an FCI occurred in magic angle twisted barriography in line with HBN, and it's the work of one of our organizers. And so the data was from capacitance measurement, where they found that, so you have some compressibility measurements, and then whenever you have compressible states, you look at how density and B field evolve together, which is this Landau fine diagram on top, and then you can interpret the different slopes that you find through the strata formula, which tells you that the derivative of the density, so on the x-axis with respect to magnetic field, on the y-axis gives you the whole conductivity. So whenever you have that slope, you could get an FCI, and there is an FCI, which is the red. Sorry, my better pointer is not working, but this would be this red line here, but unfortunately it doesn't go all the way down to zero fields. And this is understood to be because there's a strong competition with a charge density wave. So here the blue line, which is vertical, so no hole conductivity. And essentially this becomes, because the Bailey curvature fluctuations are strong at a small B field, but smaller at smaller B field. Those Bailey curvature fluctuations favor a charge density wave at smaller fields. Since then, we've had fractional chain insulators in the absence of a magnetic field, first in twisted MOT2. The evidence was first optical and then through transport measurements, again with the same hysteresis loop that we had for the integer case. In terms of theory, maybe I don't go through that again. I talked about that earlier. It's a little bit hard to know. I think the theory of why this angle came after the fact. Before that, people would have assumed that a smaller angle was necessary. And then quickly after, there was also an observation of an FCI in rhomboedral graphene aligned with hexagonal boron nitride. And there, the theory is actually, I think, much more complicated and still ongoing. So the first thing, which is maybe not a problem, is that the single particle band without interaction is not a Chan1 band, but a Chan5 band. But that can be worked out through by doing some Hartree-Fock and find, at the mean field level, including interaction at the mean field level, the Chan band is a Chan1 band, not Chan5, so that's okay. But then there are a lot more puzzles about notably the importance of the moire potential, because the FCI was found in a regime where this moire is actually really weak. And other questions that I won't delve on. And yeah, this brings me to my conclusion. So there are topological flat bands in moire materials. They host many quantum Hall phenomena, including ferromagnetism, quantized anomalous Hall effect at integer and fractional filling. And maybe a large message of this is that typically, beyond the bandwidth and the topology, the quantum geometry of moire band also plays a huge role in stabilizing some of these phases and in determining their properties. So I thank you for your attention, and I'm happy to take questions.
We have time for a couple quick questions, so I'm going to go there first.
Thank you for the talk. I just have one question about the ED calculation of the 2/3 fitting. So is that calculation performed on a spinfold model?
Yeah.
I think it's in the previous slide.
Okay. So I thought you meant the
There's a numerical.
Yeah. So okay, yes. So there's a caveat. So what I'm showing here is so this one is actually spinful, because you can see I wrote S is the
So are you able to tell whether this is the 112 happening state, or if it's the other state?
Just from the spin polarization, actually. So we have total spin is a good quantum number in the system. Yeah. So we just see where the ground state is, and then we just recover the value of S squared, and we can say that. So here this is a situation where this is the ferromagnet. I think so. The colors are not really clear. It's not really helpful here. But here, you cannot really see them. So here, this is the ferromagnet, but this is another regime where this is a singlet.
Then if it's the ferromagnetic state, then should I expect magnon excitations, which are presumably gapless?
You're right. So then it's probably the singlet. Sorry. I'm clearly I cannot see with the colors. Maybe if I look on the screen here. Oh no, this is terrible. Yeah, I didn't pay attention when I took the picture from my paper. I'm going to check and get back to you, but clearly if there's a gap, it's the singlet. You're right.
Okay, thank you.
Yeah, if there's a gap, and I'm showing all spin sectors, because here, like on the left, on the left, I'm sure that this is the ferromagnet, and there's a gap, but because I'm just showing the spin polarized sector, not all spin sectors.
Anyone else? Any more questions?
Hey, thanks so much. That was great. About the quantum Hall ferromagnet. I heard a little bit about at APS of people talking about nematic order coexisting with quantum Hall ferromagnet. Is that something that seems plausible that could be mediated either by interactions or just by like strain or substrate effects or something like that?
I'm not going to
Just
be able
curious if
to
it-
make an intelligent answer
Just
to
curious
this.
if it can.
Travel to APS, probably.
Nice. I had another very quick question also about the ED. Are there any of these calculations? Do you take screening into account?
Yeah.
Does that
Yeah.
is that the value of that parameter that matches, that works, that kind of pops out of the calculations? Does that correspond to some physical mechanism that is kind of intuitive? Like does that basically how sensitive are the results to?
It's not super
I
sensitive
see.
to screening. Yeah, so it's taken into account, but it's not extremely
I
sensitive
see.
to it.
Just curious. Okay, thank you.